Hi, I'm going to talk about a couple of very basic concepts from graph search. I'm not going to talk about the specifics of breadth first and depth first search and how it works, but I am going to look at one concept from breadth first search that applies to pretty much most of the graph algorithms out there. And I'm going to show how closely related breadth first and depth first searches are. This doesn't come across in the standard treatment of both of these algorithms, which is why I thought it would be good to present this. So to start out with breadth first search, you know how it works. We've got a source vertex and a bunch of other vertices that we then traverse. And the idea is you could think of this as the hello world of graph algorithms. It's like the basic concept that we study. It's like the first algorithm that you study in graphs. So the assumption is we've got an adjacency list representation of the graph. We are given a starting vertex and we want to find out, first of all, which other vertices are reachable from the source vertex, and also which vertex, the order in which the vertices can be reached. So we want the minimum distance from the source vertex to all the other vertices in terms of the number of edges. So the standard way is, to start with all the neighbors of S, and then the neighbors of the neighbors, and then basically continue in that form. So this forms kind of like a wave that propagates away from S. So in order to do that, we start from S and we say, okay, which are the neighbors of S? And then we say, let's say it's vertices 1, 2, 3. And then we first process vertex 1, vertex 2, vertex 3, and then we go to the next. So what does processing vertex 1 mean? It means that, hey, the next vertex that I'm interested in is vertex 4. So we've got to keep track of which vertex to process. When we process vertex 2, we'll also say there's vertex 5 that we need to process. So the key data structure that's used out here is essentially a first in, first out queue. And if you look at the pseudocode for breadth first search, I'm going to skip over the details, but it's going to look something like this. So we initialize Q to be just the source vertex, and then while the Q is not empty, what we'll do is let's say vertex U is remove element from Q, and for each V such that UV belongs to E. So I could write it like this, or I could say for each V that is a neighbor of U, if V is not visited, then Q is Q union V, and V dot visited is equal to true. Okay, and I'm not going to talk about the visited flag and stuff like that, but what I want to talk about is the running time of this pseudocode. So if you were to look at it at a very high level, you could say, okay, I have two nested loops. The first while loop is iterating while the queue is not empty. And if you think about how breadth first search works, in case we have a fully connected graph, every vertex is added to the queue once and is removed from the queue once. So this particular while loop iterates exactly V times, right? What about the for loop inside? So the for loop is looking at all the neighbors of vertex U. And you could make the statement that, okay, in the worst case, all the edges in the graph come out of my particular vertex U. So I could say this is big O of E. And I could say, okay, two nested loops, one is big O V, one is big O E, and we end up having a running time of big O V times E. which is roughly big O V squared for a fully connected graph. Not roughly, it's exactly V squared. But if you think about what's happening out here, the first time we initialize Q with S. So we've pulled out S from the Q, and then we are looking at all the neighbors of S. So that's these guys. And then we've completed the processing of S. And then we look at 1, and then we say, okay, it's got this neighbor. Then if I look at vertex 2, it's got this neighbor. And well, vertex 2 also has these edges, but they're connected to vertices that are already visited, so we're not going to worry about that. Similarly, vertex 3 has edges, vertex 4, vertex 5, and that's basically the processing that happens. So if you look at these green highlights that I've done, essentially what you'll find is those nested loops, the while loop over all the vertices and the for loop that goes over all the neighbors of the vertex. They are essentially combining to traverse all the edges in the graph, right? So even though it might look like our running time is V times E, if we combine these two and think about what's happening in the graph, the running time is in fact just big O of E, right? And that is something that I wanted to highlight, because this particular pattern where we say for every vertex and for every neighbor of that vertex, we see that multiple times, but the minute you see that, you should recognize that, hey, this is simply iterating over all the edges. But rather than saying for every edge in E, because there's no order of edges, it is enforcing a particular order, right? So that's one insight that I wanted to highlight, that essentially what we're doing is iterating over the edges. So even though we have a nested loop, the running time is just big O of E. And the second thing is it's enforcing an order in which we process the edges. So it doesn't look like it, because we're looking at a queue which is full of vertices, we're looking at neighbors of those vertices, but essentially what we're doing is looking at the edges. So that's the first part that I wanted to talk about. The second thing that I wanted to talk about is the relationship between breadth first and depth first search. So if you think about how breadth first search worked out here, we started, I'm going to draw, I'm going to create a table out here where I have the Q and the U that I've just pulled out, right? So to begin with, my Q is simply the vertex S. That's the initialization. So inside the while loop, my U is now S. And as I process the neighbors of S, I am going to add vertices 1, 2, 3. In the next iteration of the while loop, I'm going to pull out 1, and my Q is going to be 2, 3, and then I'm going to add vertex 4. Similarly, the next time I'll do 2, this will be 3, 4, and I'll add 5, and so on. When I go to vertex 3, 4, 5, there's nothing being added. But what you'll see is that I am consistently pulling things out from the front and adding new vertices to the back. That's why it's a first in, first out queue, right? So if we have an implementation of a queue, we can just use that as is and implement a breadth first search. Now what I want to talk about is a depth first search. So out here what happens is, suppose I have the same structure as before. In a depth first search, what we're doing is we start from S and then we are going to visit one of its neighbors. And what does visiting mean? So S has not been processed yet, but the minute we go to a neighbor, we then do a depth first search from that neighbor. So then from this guy, maybe I'll do this. Well, not maybe, that's the only thing I can do. And then let's say I go to this guy and then this guy, and then I backtrack, I do this guy, and then I backtrack, right? So now here's something interesting. I'm going to give the same labels as before. And if I think about the order in which I have visited a vertex and the order in which I finish visiting a vertex, what I'll find is I start with S, then I have S and 3, then I have S, 3 and 2, S, 3, 2, 1, S, 3, 2, 1, 4, and then S, 3, 2, 1 again because I've completed 4. S, 3, 2, S, 3, 2, 5, and then it unrolls. S, 3, 2, S, 3, S, and then we are done, right? So as you can see, all of the action is happening at the tail of this list, right? So whatever we put in at the end of the list is the first one to be processed, right? What that means is I can simply, well, what does this mean? Like, what data structure gives me this behavior? So I'm putting things at the end and I'm removing them from the end itself, right? That's simply a last in first out queue, which is better known as a stack. What that means is that in the pseudocode for depth first search, if everywhere I see a queue, so remove element would just be a pop, and adding an element would just be a push. And that's it. A depth first search is exactly the same as a breadth first search, as long as we replace a FIFO queue with a stack. And that's something that gets glossed over because of the way depth first search is typically presented. And you're probably thinking, hang on, we don't use stacks in depth first search. Typically what you'll have is something like DFS, which then calls DFS Explore. And what DFS Explore does is it recursively calls DFS Explore. Okay, so where's the stack out here? Well, the stack is implicit in this recursive call. Recursion implies stack. Because as you see out here, when I start with S, I'm processing 3, so that's a new recursive call. I'm processing 2, I'm processing 1, I'm processing 4. Then once 4 has completed, I roll back, I return from that last bottom level call in the stack, and then I'm processing 1. So if 1 had additional neighbors, I would process those. Then I come back to 2, and then I push 5, or I execute a call to 5, and then I come back. So there is a very good reason why DFS is structured like this, but the problem is once you look at the algorithm in this manner, you lose sight of the fact that what you're doing is essentially a breadth first search with a stack instead of a queue. All right, so that's kind of what I wanted to talk about. Like I said before, this isn't an overview of breadth first or depth first search. My assumption is you've already seen those algorithms, but I wanted to give you an insight into two key aspects. One is thinking about breadth first search as an exploration of the graph in terms of its edges, and the pattern where you're iterating over all vertices and all neighbors of those edges. And the second is, if we just replace the data structure of a queue in a breadth first search with a stack, what we get is a depth first search. All right. And you should recognize that when you're doing recursion, not just in depth first search, basically anywhere, you're essentially working with stacks. All right. Hope this was useful. Happy to hear your feedback, and thank you.